Okay, so question 3 is gear systems and turning moments. And we've got two gears, gear R and S. Gear S rotates through 2 revolutions. So we're going to turn this one. And it says how many will happen by gear R. So what we do know then is this larger gear will produce more revolutions than the driver gear. So the one being driven, we know that this is going to go up. And we know that we've got 2 revolutions on this. So what we've got to do now is just find out, well, how many more revolutions will you do? And we look at the gear ratio. So we've got 20 to 60. So that's going to be 3 to 1. So this will go 3 times more revolutions. So get your gear ratio, 20 to 60. Simplify it, is 1 to 3. Gear R will turn 3 times more revolutions than S. So 2 times 3 is 6. Next one, we've got gear S is being turned around. What's going to happen to gear T? Well, we can see if we've got to force this way, it's going to force gear T down. And then the next part is, it's going to say gear S has 60 teeth. Okay, so I'm going to just transfer that to the diagram. And on each gear T, these are 2 millimeters. So we know each of those is 2 millimeters. Gear S moves through 1 complete revolution. So that's going to be 60 lot of teeth. And each of those teeth are 2 millimeters. So we know we're going to get 120 millimeters. And we've already said, well, if that's turning this way, it's going to force this one down. So we're after 120 millimeters down. That's D. On to the next one. So fat, moody dinosaurs. And that's the perpendicular distance. So it says calculate the turning moment of the 70 Newton force. So here's the pivot, and we know that this will have a clockwise turning moment, and it tells you what to use. You've just got to put the values in. So we want to work out this. The force is 70, the distance is 0.40. There's no unit changes there. Plug it in, and what's the unit going to be? Well, in this case, we've got newtons times meters, and as you know, in terms of maths, if I did A times B, I'd write it as AB. And this is going to be, Newton meters. So 70 times 0.4 is 28, 1 mark, Newton meters mark. Next part, we've got a worker using a wheelbarrow to move some sand. The load is equal to the total weight of the sand in the wheelbarrow. Okay, and we can see that that's acting there. And here is the axle. So we've got a pivot there that they're lifting up around. The effort that he's got to do to lift it, why is the effort smaller than the load? So the whole point of using a turning moment, I used the example with you on a door and a pivot. I can't quite remember which students I used for this, but I got them to place their hand right next to the pivot, right next to the hinge, and I put my little finger there, and we worked out that with my little finger, if they have no advantage in terms of the distance from the pivot, they couldn't shut the door. So explain why the effort is smaller than the load. So the first part is, this is loads further away than the load. So if I just get rid of these arrows, we can see if here's the pivot, that's where the effort is at this point here. The load is here, well, that's less distance compared to that. And we know that the turning moment equals the force times the distance. So we have a mechanical advantage in increasing the length of the lever. And this gives a mechanical advantage as less force is needed. So, and again, it's just one of those questions where get your formula and try to work out what's going on. And we've got, well, we know that the moment is force times distance. Talk about that. Done. Some sand falls down and sticks between the wheel and the axle. Why is it harder to push? So we're going to have to talk about friction. We've got some sand, and that's providing additional friction. So there will be more friction, and this will transfer more wasted heat energy. Done.